In this video, we'll classify the groups of order 8 up to isomorphism. Our result is going to be that there are 5 groups, 3 abelian ones, C8, C4 cross C2, and C2 cross C2 cross C2, also known as the elementary abelian group of order 8, and then the dihedral group of order 8, and also the quaternion group. So required knowledge for this proof is going to be Lagrange's theorem. So let's suppose that G is a group of order 8. By Lagrange's theorem, any element of the group that is not the identity will have order 2, 4, or 8. Suppose that all elements have order 2. Well, then I claim that G is abelian. Why is that the case? If A and B are elements, then AB inverse is going to be B inverse A inverse, which is BA, since these elements are ordered 2, so their inverse is just themselves. But then the same goes for AB inverse, so AB inverse is equal to AB. And then this here, we just have the group is abelian. So let's take A in the group that is not the identity. Well then, this subgroup is a normal subgroup, since G is abelian, and it's isomorphic to the cyclic group of order 2. Let's choose B in the group, such that B is not in this cyclic subgroup. So B is not the identity or A. Then the subgroup generated by A and B is going to be the set, the identity A, B, and AB. Why is that the case? Well, we can just consider every single possible string of A's and B's, and because it's abelian and because it's order 2, you can always commute them and just reduce any string of A's and B's into one of these forms. But we can see this is going to be isomorphic to the direct product of A and B, the cyclic groups generated by A and B. Why is that? Well, we just consider the natural isomorphism between these two groups, where the identity is sent to the identity in both parts. A is sent to A identity, B is sent to identity B, AB is sent to A, B. Now we're going to finally pick, this is a group of order 4, because it's just C2 cross C2. So let's take C in the group, but not either of these. Now C is going to be an element of order 2. By similar logic, we get G is isomorphic to A cross B cross C, which is just C2 cross C2 cross C2. This is the one that is also called the elementary abelian group. Well, let's suppose now, so we've done the case that all elements of order 2, so let's suppose there's an element in the group such that the order of the element is more than 2. Well, then it has to be 4 or 8. But if we have an element of order 8, then its square will have order 4. Therefore, there's going to be an element in the group such that the order is 4. I'll call this element A, actually, to keep with how we did it in the previous case. So now, C4 is this cyclic subgroup, which is an index 2 subgroup and hence a normal subgroup. So let's take some B in the group, but not this cyclic subgroup. Well, then I claim that B squared is in this cyclic subgroup. Why is that? Well, the quotient group here is a cyclic group of order 2, so if we consider the element of the quotient group B quotient A, its square is going to have to be B squared A, which is also going to have to be A. Therefore, B squared is in the cyclic subgroup generated by A. So that's the reason why we introduce this. B squared is going to be the identity A squared, or A cubed. If B squared is the identity, is A or A cubed, well then we're going to have order of B is 8. And we have a order 8 subgroup, which is isomorphic to the cyclic group of order 8, but that's the same size of G as G, and therefore G is C8. Instead, if B is the identity, or A squared, well then BAB inverse is going to be in the cyclic subgroup. Why is that? Well, the cyclic subgroup is normal, as we've remarked on. So BAB inverse is going to be E a squared or a cubed. I'm just going to write this as it's equal to A to the I for some I, and we'll see why in a minute. Now BA B inverse squared is going to be B squared A B to the minus 2. You can see that by just writing out the entire thing and seeing that the B and B inverse cancel. But also B squared A B inverse B to the minus 2 is going to be B A B inverse B inverse, which is B A to the I B inverse, which is B A B inverse to the I for similar reasons. So that's going to be A to the I, which is A I squared. Also, we remark that B squared is in this cyclic subgroup. It's a similar reason. So B squared A B to the minus 2 is going to be equal to A. So A equals A to the I squared. So I squared is going to be equal to 1 modulo 4. So I is plus or minus 1 modulo 4. If I equals 1, then BAB inverse is equal to A. So BA equals AB, and G is abelian. So we now have different cases for what B squared is. If B squared is the identity, then G is going to be the direct product. Then G is going to be this direct product, since G must just be A and the coset of B in A, and that's isomorphic to C4 cross C2. Now, if B squared equals A squared, then BA inverse squared is the identity. That is just direct from rearranging that. So we're in a similar kind of case here, but we've just replaced B with BA inverse. And by similar logic, we just get that G is this direct product, which is isomorphic to C4 cross C2 for similar reasons. So if I equals minus 1, then BAB inverse is equal to A inverse. And remember, we now have these two cases on B again, B squared again. So if B squared is the identity, then BAB equals A inverse. Let's just have a look at this subgroup generated by A and B. Well, A to the 4 is going to be B squared, which is the identity, and BAB equals A inverse. And that's just the presentation of the dihedral group. And therefore we can conclude that G is D8, since this is a subgroup of the same order as G. And if B squared is A squared, let's have a look now instead at this presentation. Now this is a presentation of the quaternion group. So G must be isomorphic to the quaternion group. Now if you know the classification of finite abelian groups, you can do the abelian part a little faster. You can just recognize that an abelian group must be a direct product of cyclic groups, and we know that CNM is isomorphic to CN cross CM if and only if N and M are coprime. So we can just enumerate all the ways we can possibly split up A to get that the abelian groups must be C8, C4 cross C2, and C2 cross C2 cross C2.